Hi, my name is Alan from the High-Speed Signal Path Group at National Semiconductor. In this video, I'll be discussing and demonstrating the LMK04800. The LMK04800 is a high-performance, highly configurable jitter cleaning clock generation for wireless infrastructure and other high-performance applications. One of the key applications is shown in the system block diagram. Here, the LMK04800 is providing multiple low-noise clocks to clock high-speed data converters such as ADCs and DACs, PLLs, FPGAs, and other high-performance blocks. In order to synchronize the output clocks to the baseband unit, the LMK04800 must receive a reference clock. This reference clock is provided by the SCAN25100 CPRI SerDes. That SerDes provides a link to the baseband unit for transferring data and synchronizing the system. In order to meet the jitter performance requirements of the system, the LMK04800 must have very good clock jitter cleaning capabilities. Here we can see the jitter requirement of the ADCs used in the system. Here, SNR is plotted versus input frequency. As you can see, at low input frequencies, the ADC's dynamic performance is limited by the noise floor of the ADC. As we approach higher input frequencies, such as 100 megahertz or above, we can see that the jitter performance will start to limit the dynamic performance of the ADC. For example, at 200 megahertz input frequency and a 14-bit ADC, we need a clock jitter of less than 200 femtoseconds in order to maintain the dynamic performance of 74 dB SNR. The internal architecture of the LMK04800 is shown in this internal block diagram. Here we can see the dual loop PLL architecture. In order to provide very low noise clock jitter cleaning, PLL1 utilizes a very narrow bandwidth loop filter and uses a very stable external VCXO or crystal. This crystal is locked to the reference input and provides a very low noise and frequency accurate reference clock for the second PLL. The second PLL utilizes an internal VCO, which provides a clock generation function. That clock that's generated is synchronized to the reference clock and fed to the clock distribution blocks shown here. So it's the dual loop PLL architecture that provides very low noise jitter cleaning and clock generation for the system. In order to demonstrate the jitter cleaning capability of the LMK04800, we have here a demonstration setup. Here we have a SCAN25100 SerDes providing a test pattern, a CPRI compliant test pattern, which is being transmitted by one board and received by a second SCAN25100 evaluation board. This SCAN25100 has the deserializer receiving the data and extracting the reference clock. That reference clock is a 30.72 megahertz clock, and we're measuring the phase noise performance on our E5052. As you can see here, we can see that the RMS jitter is about 5.2 picoseconds over an integration bandwidth of 100 hertz to 20 megahertz. In order to demonstrate the clock jitter cleaning capability, we'll now switch over to measure the output clock of the LMK04800 running at the same frequency. So in this configuration, we're now feeding the 30.72 megahertz recovered clock to our LMK04800 board. The clock is then used to synchronize the first PLL and VCXO, external VCXO. This VCXO is 122.88 megahertz. That provides the very low, close-in clock jitter cleaning for the second PLL, which has an internal VCO that's running at 2.94912 gigahertz. That internal VCO clock is very low noise and is divided down by the clock distribution section of the LMK04800, and we now have a 30.72 megahertz LV Pecco clock being fed to our E5052. As you can see on the screen here, we have about a 10 to 15 dB improvement in the phase noise up to 10K, and above 10K we have even better improvement of 25 to 30 dB. You can see here the RMS jitter is about 217 femtoseconds over an integration bandwidth of 100 Hertz to 5 megahertz. We can also see down here that we have a very low broadband noise floor of about minus 159 dBc per hertz, which is excellent performance. So as you can see, the LMK04800 provides very low noise, jitter cleaning, and clock generation for wireless infrastructure applications. For more information, please visit national.com/timing, and thank you for watching.